In this video we're going to do some more modelling, and similar to the last video I haven't read this question, so we're going to be problem solving it live, similar to the last one. Okay, the temperature on a particular day can be modelled using this function. So big T, temperature, little t, time, -3 cos pi t on 9 plus 18 between 0 and 18. Alright, T is the time in hours after 5 AM. Alright, so when T is 1, we're at 6 in the morning. Yep, all good. Temperature is in degrees Celsius. Oh, okay, good. Now don't get tricked here. I know that we said before we couldn't do derivatives if things were in degrees. Well, we need to, that was degrees of angles, okay? This is degrees Celsius, so all good, don't trick yourself. For the remaining 6 hours of the 24-hour period, the temperature remains constant. Okay, so that means that after this 0 to 18, then we're going to flatline at that constant temperature. So once again, let's just quickly analyze before we get started. I've got an A here. It is -3, so my amplitude is 3, but the negative means it's flipped. So again, quick little sketch of this. I always like to do a quick little sketch before we start. I've got a K here of 18, so that means if I better sketch this even differently, exaggerate it even more. I've got a K way up here at 18, and my wave has an amplitude of 3. So I'm going to go to 21 is going to be my maximums, and 15 are going to be my minimums. But we have to remember, am I starting at a max or a min? Well, normally I'd be starting up here, and I'd be doing this. Whee! However, my A is -3, so I'm actually going to be starting down here at a minimum, and we're going to be going up, down, etc. Now, we still have a B transformation, as we did before, so I'll do that in red. There's my B transformation. Oh, what did I write? Okay. There's my B transformation of pi on 9. So just quickly, I might even just do it here. My period is going to be 2 pi on 9, which means my period is going to be 18. So I'm going to have one full wave after 18 hours. Well, look at this. Already, I've already got more than one full wave, so let's just quickly draw it. I'm only going to have one full wave. There we go. So that is 18. Now, no B transformation, so all good. We've actually already started doing our job here of sketching it. It then says we're going to flatline. So, okay. All the way up to 24. So we already got a pretty good idea here. We've got a pretty good idea. Y equals 18 as my equilibrium line. We've got a pretty good idea of what we're looking at. So let's just divvy some of these data points up as soon as we can and then work out what they mean. Alright, we're at 0, and based on our K and our A, I'm going to be at 0 and 15. Based on this one over here, I've got a full period at 18, so I'm going to be at 18 and 15 again. And then this maximum happens halfway between these two, so that'll be at 9. And again, based on my K and my A, I'm going to be up at 21. Alright, and I've got 2 equilibrium points. I'll quickly do those in green. Here we go. These points are halfway between mins and maxes. So halfway between 0 and 9. So that's at 4.5 and 18, because that's my equilibrium line. And then halfway between 9 and 18 is 13.5 and 18. Right, this seems pretty good so far. Then the last thing we have for our rough sketch, again, just I don't even know what the question wants from us yet. I'm just having a rough idea of what it looks like. If I was to flatline here, my Y value is sitting down here at 15, so this flat line would be Y is 15. Up all the way up until we get to the 24-hour mark. All right, so what are we looking at? Temperature in degrees C, and then my x-axis is just the time in hours. Now, I didn't spend a hell of a lot of time sketching that. I was just trying to visualize where some of these points are before I even start. All right, part A, calculate the temperature at 8 a.m. Okay, well, clearly I know that I'm going to be sitting somewhere up here. Okay, but hold on a second. That can't be right. That's when T is 8. Well, what I want is 8 a.m. And this question says T is the time after 5 a.m. So what A is really asking us is, what is temperature at 3? So we could simply put that straight into our equation. -3 cos of pi times 3 on 9 plus 18. -3 cos pi on 3 plus 18. Alright, as always, quickly whip out a unit circle. Pi on 3 is going to be somewhere over here. Pi on 3, well, let's draw an exact value triangle again. Oh, that triangle's a bit suspicious, but that's okay. It's a bit rough. Pi on 3 is 60 degrees. And 60 degrees is going to give us a cos, as we saw before. Cos is adjacent over hypotenuse. So that means cos of pi on 3 is going to give us positive 1/2. So -3 times positive 1/2 plus 18. -3 on 2 plus 18. Easiest way for us to do this now is to convert this 18 into 36 on 2. So 36 on 2 take 3 on 2 is 33 on 2. Alright, so 33 on 2. Now it's a real life scenario, so let's actually just quickly turn that back into a number. Half of 33 is 16.5 degrees Celsius. Looking at part B, determine the times of the day at which the temperature is 20 degrees. Okay, now note it says not above 20 degrees, it says 20. So if we look here, we're at 20 somewhere here. So it looks like somewhere when T is 8 or T is 10 or somewhere around that time. Now that doesn't mean 8 a.m. and 10 a.m. It means 8 hours after 5 in the morning or 10 hours after 5 in the morning. So the way that I am going to approach this is, where is T of T equal to 20? So just, where is this whole equation that we had before? Pi on 9, T plus 18. Where is that equal to 20? Now we could go ahead and rearrange all this, and if we do, we're going to get something with negative 2/3, and it's not really going to be very useful. So instead of trying to do all this by hand and not really getting anywhere, it's looking like a calculator question. So let's just use a calculator skill. I can, with angles, use solve n, and solve n is what we're going to use when there are a number or multiple solutions. So all I need to do is type into my run matrix of my calculator solve n for where this equation is equal to 20. Now you have to remember, in your calculator you're not going to be able to write t, you're going to have to put an x into your calculator, and then it'll probably say multiple solutions might exist. Yep, all good. Now here's some of the possible answers that it's given us. We've got some answers of -42, etc, etc. Now let's think about some of these numbers that make sense. My numbers have to be between 0 and 18. So all I'm going to do is scroll through my answers until I find some answers that are logical. I've got one here at 6.59 hours. Then I've got another at t equals 11.41 hours. So yeah, that seems about right. Looking at our graph of this seems logical. I guessed between 8 and 10, a little bit off, but that's okay. Now, we would still have to convert 0.59 hours back into minutes. So 0.59 of 60 is going to be 6 hours and 35 minutes. Again, according to this, I'm going to the nearest minute. And then for the next one, what is 0.41 of 60 minutes? And that would be 11 hours and 25 minutes. So those are the times to the nearest minute when we would be equal to 20. So there's our calculator skill for this question. Part C, we'll do that in yellow over here. Determine dt. Okay, nice and easy. dt is equal to, well, just doing the derivative of that function. Derivative of cos is negative sine, while negative of -3 is positive 3. Sine, move it over a little bit. I don't touch absolutely anything about my angle inside the bracket. I'm going to times by the derivative of what's inside my bracket, and the 18 is going to go away in the bin. So that means dt is equal to 3 pi on 9 sine of pi on 9 t. Now, of course, I don't want 3 pi on 9. I would rather just write this as pi on 3 sine of pi on 9 t. Done. Part D, determine the rate of change. Pause, rate of change, derivative. Yep. At the times found in part B. Correct to 2 decimal places. Well, this is screaming calculator. So we've got our part B over here. We've got our part C a bit further over. All this question is really asking you is what is dt at t equals 6.59 and t equals 11.41. Now, clearly, calculator skill question. So all I'm going to go is what is, and actually there's 2 ways of doing this. If we trust that our derivatives are very good, what we can do is simply substitute these numbers straight into here, which is perfectly fine. So let's have a look at if we did it that way. Let's do the first one that way. So I could say dt at 6.59, apparently 2 nines, at 6.59 is equal to pi on 3 multiplied by sine of pi on 9 times 6.59. And I can put that in my calculator and get an answer out of it. You get an answer of somewhere around 0.78 degrees Celsius per hour. Now I'm going to do the next one here. I'm going to do the next one in green. So we said t equals 11.41. Now, if I didn't trust my derivative, maybe I'm a bit bad with derivatives, but I'm pretty good with my calculator, I could simply go ddx of -3 sine pi on 9 t plus 18, so the whole original equation, where x is equal to 11.41. And what your calculator will do is it will do the derivative for you, then it will substitute 11.41 into your calculator, and then it will give you an answer for what this is equal to. What is the derivative at 11.41? Which is an answer of negative 0.78 degrees Celsius per hour. So clearly at one point our graph is increasing, and at the next point our graph is decreasing, and yeah, Let's have a look at it. Clearly, we knew that. At this point, my graph is increasing, and then over here, my graph is decreasing. So that just further solidifies exactly what we thought would be happening. All right, so as before, it's just a combination of skills all rolled into one that you need to have fluency with, and these modeling questions will go from being complex to actually feeling quite simple.